Hello, Chem 1B. This is Chapter 19, Lecture Video 6, and we're going to be talking about E cell, or the cell potential under non-standard conditions. So, standard state for voltaic cells is always 298 Kelvin. In addition, we're at 1 molar for any concentrations, or if we're talking about pressures, gases, we're at 1 atm. So, these are what the conditions are for standard cell potentials or reduction potentials. So if you are looking up a reduction potential in a table anywhere, it's under these conditions. Now, what happens if E cell is not under standard conditions? I can tell you that very rarely am I under those exact conditions for when doing experiments. It's very rare to be at exactly 1 molar for your concentration. So what do we do if those conditions aren't the conditions we're under? So we know this is the formula for non-standard delta G. It's the standard delta G plus RT, ideal gas constant, 8.314, times temp in Kelvin. And this is our reaction quotient. Oops, quotient. Well, we also know some new equations here that we learned in the last lecture video, that delta G is equal to negative NF E cell, and delta G naught is equal to negative NF E naught cell. We really learned this one, but it also applies for the non-standard version. That is the relationship between delta G and E cell, or delta G naught and E cell. Now, if we take these and we plug them into this original equation, we can derive a new equation that involves E cell, like so. Now, we usually want to get this guy by itself, so we'll divide both sides by negative NF. And negative NF cancels there, but we're left with it, really. Here, I should write it better. These two cancel, and these two cancel. And what we're left with looks like this. And this is known as the Nernst equation. We have E naught cell here, standard conditions, non-standard conditions over here. Here is 8.314 joules over moles times Kelvin. This is temperature in Kelvin. This is Faraday's constant, 96,485 joules, moles, Kelvin. And this is moles of electrons transferred in the redox reaction. And this is still our reaction quotient. And again, this is known as the Nernst equation. It allows us to change our E cell value, or account for it in terms of different temperature or different concentrations or pressures in the system. So if we're not perfectly at 1 molar for everything, well, we have to use this equation. Or if we're not at 298 Kelvin. So again, this is known as the Nernst equation, named after the dude who came up with it. It lets us calculate E cell, not E naught cell, but E cell, non-standard. And again, remember that Q is just our non-equilibrium concentrations of the reactants and products over reactants still in the calculation, taken to the powers of their stoichiometric coefficients, which means we need to balance our redox reaction before we can actually use this equation. Because Q requires all those stoichiometric coefficients. We need to know what the values are so that we can put them as exponents. Again, the book uses another version, and I hate this version because this one only works at 298 Kelvin. Again, I will not be giving you this one. I'm going to give you this one. So I'd get used to using this equation as opposed to this one. It's mainly just a pet peeve thing. It's definitely an opinion thing. I just don't like this equation, the bottom one. So let's do a problem. All right, calculate the voltage generated for the following reaction when we have this concentration of aluminum 3 plus and this concentration of I minus. So here is the balanced redox reaction, all given for you. First, we need to calculate E naught cell. Now, we can do that by figuring out, hey, what's being reduced, what's being oxidized in this reaction. If we split this up into the half reactions and do our calculation, you know, cathode minus anode, looking up the reduction potentials, then we should get 2.2 volts. You should go back and confirm that you know how to do this part. But after that, we can now plug this into the Nernst equation, right? So here's our E naught cell that we calculate. This is R. This is T. Anytime you're not given a temperature in any of these problems, we're always going to be assuming 298, just like in the thermodynamics chapter, chapter 17. We should also try to figure out how many electrons are being transferred, and we can do that by looking at the half reactions, right? So if we look at Al solid going to Al3 plus, I know that 3 electrons had to have been given off for that to happen. At the same time, I have I2 solid going to I minus. That would have required 2 electrons to occur. And this is aqueous. Well, 3 and 2, we need to multiply these guys out. I'm going to put a 2 there, a 3 there, so that they equal the same number. 3 times 2 gives me 6. So I have 6 electrons here, as you can see here for N. And then this is just Faraday's constant as well. Now here's Q. We know from the reaction here that the reaction quotient is products over reactants, but the products here are solids, and as we have learned quite hopefully well, solids don't get involved in Q or K equations. So this equation should just be the aluminum 3 plus concentration squared times the I minus concentration to the power of 6. And we're given I minus's concentration, so that just goes there. And we're given aluminum's concentration, so that just goes here, as you can see here and here. At the end of the day, now this is just a plug into the calculator and solve for the value. So if we do that out, we get volts, and our E cell is 2.36 volts. All right, so let's continue on. So let's talk about this a little bit. All right, how does increased concentration of products affect E cell? Well, let's look at Q here, right? Q we know is equal to products over reactants. So if I increase the products here, Q is also going to increase. What does that do to our equation, though? Because if Q gets bigger, then this whole term gets bigger. And since we're subtracting this, the larger this value is, the smaller our E cell is. It's going to reduce the cell potential as products are higher. The opposite is also going to be opposite, right? So if we increase the reactant concentration, Q is going to go down. Our whole term here is going to go down as Q goes down, which means E cell isn't going to go down, it's going to go up because we're subtracting off a smaller value. All right. So let's do an example that's kind of important. We can use the Nernst equation. We can use concentration really to generate voltage without anything else happening. So if we look like at a voltaic cell, where we put two different concentrations of nickel 2 plus in two different cells and put nickel electrodes in each one. This concentration is going to want to go down, this concentration is going to want to go up, and this will continue to happen until the concentration of nickel 2 plus in the two separate cells are equal. The concentrated solution, how do we get this guy to go down? Well, we got to get rid of the Ni2 plus, right? So Ni2 plus must, in this case, the 1 molar solution must go down to Ni solid. Well, how do we do that? We add 2 electrons to this guy. At the same time, the aqueous solution, this needs to go up. So how do we do that? We got to form more of it. In other words, we want it to be a product. So I need to be forming that. That means I'm going to be oxidizing my nickel to get this guy to go up. So let's look at an example of that, right? We have a voltage here, even in this scenario, and it's the same setup as the previous slide, right? We have one solution with a Ni2 plus, right, in here, concentration of 1 times 10 to the negative 3. And then we have our darker green solution. Nickel 2 plus is a green solution. And it's at 1 molar. There is a voltage, even though we still have the same half reaction. In both cases, we have nickel solid going to nickel 2 plus 2 electrons. And on the other side, we have nickel 2 plus 2 electrons going to nickel solid. These are aqueous. If you look at this, the E naught cell here has to be 0 because these both have the same reduction potential. Is equal for both the cathode and the anode. Because they're the same half reaction on both sides. Which means if they're equal, E naught cell has to be equal to 0. Which is weird because we're still generating voltage. The answer is, why are we generating voltage? Because these are not at 1 molar concentration for both half cells. And when we're not at 1 molar concentration, we're not under standard conditions. This is a non-standard system. So, knowing all that, we can look at this, and this is what's known as a concentration cell. Concentration cells are where we have voltage stemming from a concentration difference. So let's look at another scenario, right? So eventually what's going to happen is, as this happens, right, as these electrons move into the cell, the nickel 2 plus in the solution is going to turn into nickel solid. So this concentration is going to go down as this reaction continues to happen. And at the same time, nickel is going to go to nickel 2 plus. Right? So we have nickel solid here. It's going to be moving into nickel 2 plus. In other words, this concentration is going to be coming up. Eventually, what's going to happen is these two concentrations will equalize to approximately 0.5 molar. It's not exactly that number, but it's close once they hit an equal point. And when that concentration stops being different, we don't have any more voltage. And this basically becomes a dead cell. Now, one of the harder things about these problems is figuring out how to calculate Q, right? Because Q needs to be products over reactants. But I mean, they're the same stuff, right? We have a nickel 2 plus concentration here. We have a nickel 2 plus concentration here. Where does one go? Does the 1 molar go on the product side or the reactant side, and vice versa? So we're going to figure that part out. So let's do an example. We're told a concentration cell is constructed with 2 solid zinc 2 plus half cells. In other words, I have, my beakers. And I have some liquid in here. And in this one, I have Zn2 plus. And then this one I have Zn2 plus. And then I got like my metal bar in here, and this is a zinc solid metal bar. And then this one I got my other metal bar, and it's also Zn solid. And I've connected them with a wire, and I have a salt bridge. All right, so all this is going on. Now, let's say this one is at 0.375 times 10 to the negative 4 molar, and then this one is at 1.35 molar. Well, what's going to happen here is we need to bring this guy, the reaction is going to try to make this guy come down, decrease its concentration, and this guy come up to increase its concentration. And this will continue to happen until the two concentrations become equal. We want to know which of these two is at the anode and what is the voltage of the cell. In other words, what is E cell for this system? Now, what you have to understand is if this guy is going to come up, we need to form zinc 2 plus. In other words, Zn solid needs to be oxidized into Zn2 plus. This concentration has to be for this guy. At the same time, if we want this guy to decrease, then something else is happening over here. We have Zn2 plus, aqueous, plus 2 electrons going to Zn solid. This reaction will decrease that concentration. In other words, this guy is here. So in other words, my product Zn2 plus concentration is the 3.75 times 10 to the negative 4 molar. And my reactant Zn2 plus concentration is 1.35 molar. Now, we know E cell is equal to the Nernst equation, right? So E naught cell minus RT over NF ln of Q. But this guy is equal to 0 because it's the same half reaction on both sides of the cell. In other words, cathode and anode's reduction potentials are the same, so 0. So we can kind of just cross that guy out. And really, E cell for this equation is equal to negative RT over NF ln of Q. And we can solve this problem at this point. So I'm going to erase all this so that we can kind of see the writing here a little bit better. So if we look at this, right, we have these two reactions, like I was showing you earlier. Now, they both have to be occurring because one's a reduction, one's an oxidation. We can't have oxidation without reduction and vice versa. Excuse me. We're forming this here. This guy has to be coming up. We're getting rid of this. We're reacting it. It's going that way. This guy has to be coming down. So again, this one is the one we want to go up. So that's this guy's concentration. This guy here is the one we want to go down. So it's that guy's concentration. We want to know which one's happening at the anode. Well, here's the anode. This has to be that one. And again, now we can just kind of plug this in. We know this is 0, like I said from the previous slide, because cell is equal to cathode, right, minus anode, and they're equal to each other, same value. And this is always true for when we have the same half reaction on both sides. So at this point, we can kind of plug in, right? We know that Zn2 plus 2 electrons goes to Zn solid, and Zn solid goes to Zn2 plus 2 electrons. Notice that we have 2 electrons being transferred here. That's where this 2 comes from. This is, again, Faraday's constant. This is our R value. We weren't given temperature, so we're going to assume 25 degrees Celsius. Products over reactants. Hey, this is the product. We said that this was the 3.75 times 10 to the negative 4. This is the reactant. This had to be the higher concentration, 0.135. Hence, reactant goes down here. Product goes up there. We can solve, and we get a cell voltage of about 0.105. All right. So these are kind of fun. I don't know. All right, so let's do another problem. We have a concentration cell. We know that because we're going from Fe to Fe2 plus and then Fe2 plus to Fe. This tells me that E naught cell here is equal to 0, which means my Nernst equation E cell is equal to negative RT over NF ln of Q. And Q, always products over reactants. Well, this is my product in this half reaction, and this is my reactant in this half reaction. So 0.000346 molar goes on top, and 2.56 molar goes on bottom. So this is my Q here, which I can kind of just throw in here. We know R is 8.314 here, and T, because we weren't given temperature, we assumed 298. F is 96,485 joules per mole per volt. And N is 2 in this case, because to go from Fe to Fe2 plus, we need to gain 2 or lose 2 electrons, and to go from Fe2 plus to Fe3 solid, you have to gain 2 electrons. So E cell then is equal to negative 8.314 times 298 Kelvin, all over 2 times 96,485 ln of 0.000346 divided by 2.56. And if we do that out on our calculator, we get 0.14114 volts, or in other words, B is our correct answer. All right, so if you have any questions, as always, please feel free to email me or come to a discussion session.